So there are food additives, food preservatives that we can add in order to help with the improved shelf life, improved food safety. There are acids that we can add, and acid, is that a bad thing? Well, lemon juice is one of the acids that you can use, or at least an extract from lemon juice. Sugars, salt, we just mentioned that. Antimicrobial agents of all sorts that can be added that inhibit the growth of microorganisms. Microwave heating, you're converting electrical energy into microwave photons. It's the same kind of energy that comes out of a light bulb. It's just higher energy. It's vibrating faster, so our eyes can't see it. And at this microwave energy, it causes water molecules to start vibrating and other similar molecules that react similarly, and it causes heat in the food. The device that creates this is called a magnetron, and you can generate large amounts of these microwaves to cook foods. And so it says heats by friction. It's not really the same as friction, but all right, I'll give them that. But it interacts with these charged molecules, causing them to heat up. It's mostly the water in your food that's heating and then continuing into the food through conduction, or if it's a liquid, by convection. Key difference between a microwave and conventional heating: there's no browning or crisping in a microwave. So there are different ways to change that. You color the food. A lot of our food, they literally have brown lines painted on them with a food safe color. And it makes it look like it came off of a grill. It's nothing but food safe paint. You can combine with conventional heating. So you have a microwave that's cooking it while you're blasting hot air through another device, through a convection oven device, and a convection microwave. You get browning. And there are things called susceptors. They are specialized materials that get really hot inside of a microwave without damaging the microwave. Stick a fork in the microwave. That's not good. It'll get hot, but it's not good. Certain materials react very poorly going in a microwave. But these susceptors actually interact with the microwaves in a way that they get hot enough to cause some browning or some other quality changes in the way the product is cooked. Microwaves don't give an extremely uniform heat distribution. So container design, food distribution in the container is very important in microwaved or frozen foods. Spinning trays where the interior part of the microwave literally spins, that's another way around it. There are numbers of solutions to the microwave problem. And there are other problems. It's not just that, but I've put in an irregularly shaped piece of food. I put in a chicken leg. All the weight is on one area, and what's happening to that meat that's down near the skinny end? Sometimes it kind of turns dry and rubbery. It gets overnuked before the rest of that chicken leg is warm. And chicken legs, as an example, don't microwave all that well. Sometimes they heat up unevenly where they start popping, and there's little mini explosions of water that gets really hot. It starts to boil and creates this little popcorn type puff of boiled gas, hot steam, that can damage the product appearance and change the sensory qualities, and can also spray garbage all over the inside of your microwave. There are problems with microwaves. Certainly you have to follow the manufacturer's instructions. Most of us have microwaves, and that has changed our consumer acceptance of microwaves. Now, keep in mind, there's two different things going on. There's the industrial microwaves used in food processing in a food manufacturing facilities, and there are microwaves used at the industrial level. And then there's products that are made without microwaves or possibly with microwaves, and they're intended to be microwaved by the consumer once the product reaches the home. And now we're going to cook it in our own microwaves. And that's a different issue. So again, I'm not going to worry about the changes. You can read this, but the world has changed. Microwaves have become amazingly popular. So I mentioned irradiation before. What is it? It's essentially exposing food to gamma rays, X-rays, or electrons to improve the shelf life and safety. Now, with the exception of electrons, which, it's the same thing as an electricity going through your electrical lines to power all of your devices. The others, the X-rays and the gamma rays, are just photons of light, the same kinds of photons that are coming out of this light right here that's making it so you can see me. The photons coming out of your computer screen that you can see the screen. They're photons. The difference in photons, if they're really low energy, that might be your AM or FM radio stations. If they're really higher energy, maybe it's the visible light. If they're even higher energy yet, the speed with which they vibrate, they become X-rays or gamma rays or ultraviolet rays, perhaps. We can't see those, but they're the same thing. They're just a photon going through the air. As soon as I turn off the gamma ray emitter or the X-ray emitter or the electron emitter, it's off. There's nothing left. Now, if I was in a nuclear bomb blast, if I was at Hiroshima when it went off back at the end of World War II, I would be covered in radioactive material. Very dangerous. But if I get gamma irradiated or X-ray irradiated, as soon as you turn off the gamma ray machine or the X-rays, it's off. I am no longer able to contaminate anybody. There's nothing on me. I am completely safe. There's nothing to spread. It's like turning on and off a light. Now, if I give enough of a dose of gamma rays to me or X-rays to me, I can hurt myself. It's dangerous to be sitting under an ultraviolet light or a gamma ray emitter or an X-ray emitter. It's dangerous because it can damage your DNA while you're under the light. You can get skin cancer from too much sun tanning, but you don't go spread that to somebody else. So with these gamma rays, X-rays, and electron emitters, UV emitters, they aren't dangerous after the food has been irradiated. They are only dangerous to whatever's under the emitter. If there's any bacteria on that food, it might kill it. That's the point. But just like any other high energy, like cooking, like microwaves, you can change things. There are going to be changes in the food. It will break bonds. It will break DNA. It will kill microorganisms. It might kill some of the cells in your food itself. It can kill insect eggs, or at least keep them from maturing into adults that can lay more eggs. But there's no heat. Even though there's energy, it's not heat. So there is this symbol, the Radura symbol. If any food is irradiated, you need to have this symbol placed on the container of food to show that it was irradiated. So again, there's gamma rays, X-rays, and other types of rays that can be used. The only thing dangerous on this slide is the source material. The machine that creates gamma rays uses cobalt-60 or cesium-137. And those materials, which are very well sealed in the machine, building the machine has some safety issues. The same thing with lots of hospital equipment, or even making cars. Making anything, there's safety hazards. So we do have to be careful with the cobalt-60, but there's no cobalt-60 in your food. You turn on the emitter, you gamma irradiate the food product, it comes out of the emitter, and there is nothing left on it. So why is radiation considered an additive? Well, my argument would be because we're scientifically stupid in this country. It is not an additive. It's lobbying and fear mongering. There is nothing added to your food. Now, the thought was, and the argument made was that it would change the nature of the food. So does boiling, so does barbecuing, so does cooking in the oven. Everything changes the nature of your food when you add energy to it. But in other countries, in a lot of other countries, they consider irradiation a process, which it is. Any reasonable, informed, scientific understanding of irradiation is it is a process that the food went through, not an additive to the food. But here in the United States, we are scientifically illiterate. We are governed by people who have political agendas and make public policy based on fear in order to sell products. And this is largely from organic and health food industries that put much pressure on to make it an additive in order to sell fear so you could buy organic products, which is unfortunate because it is a food safety issue. But by law, if it's irradiated, it does require the Radura symbol, implying that there's something in that food that's radioactive, which is a big pile of BS. Now, 52 countries at the time of this, I think it's north of 52 now, have approved radiating food. Netherlands has been a major user from early on. Foods do not become radioactive, but there are things called URPs, unique radiolytic products. And again, scientists are really bad communicators. URPs, unique radiolytic products. Oh my God, there's radioactive stuff in my food. No. All that means is when you treat a product, a food product, with high energy radiation, it does break down the food molecules. Some of the molecules are broken down into unique things. Same way if we cooked it in the oven, same way if we blanched it, the same way if we microwaved it, the same way if we sun-dried it. Any of these other techniques create unique processing products, all of them. And there's huge overlap between cooking and unique radiolytic products. It just means that the food product experienced some sort of energy. That's all it means. But because it has radiolytic in there, it scares people. Some foods don't do well. We've already talked about things like beans. String beans don't do well under blanching because they get mushy. Spinach gets soggy. There are lots of foods that either do really well or don't do really well based on one of these processing product or techniques, processes we've talked about. Well, some foods don't do well with the irradiation. Pears get mushy. The breakdown, it breaks the interlinking of the chemicals that give the texture to a pear. And as those break down with some of these high energy bursts, the pear gets mushy. Okay, pears aren't a good candidate for this technique. Milk reacts with oxygen. The milk fats react with oxygen inside. You're basically causing a chemical reaction, and the milk fats turn rancid. It's a reaction that does not go well. So irradiating milk doesn't go well. Fine, pasteurize the milk. Use the irradiation on products that do handle it well, that do get improved shelf life, improved food safety. And there are lots of products that do improve with irradiation. So it's not just foods, but there are lots of things that are irradiated. Pharmaceutical products like plastics and disposable items in hospitals and clinics. Things typically destroyed by heat. I'm not gonna worry about that. Packaging materials. So I've got food cartons. Irradiate the food carton before you put the food in it. So now I know I have a sterile carton, or at least a sanitized, it's not sterile, that's not an inappropriate word. You've sanitized or cleaned the carton with some irradiation prior to putting the food into it. Some issues, wastes. There's hospital radioactive waste, research lab waste. There are lots of things that we do have to be concerned about. If I'm using a radiation producing material, even though it's safe on the food, how am I going to dispose of that machine? There are the parts to that machine. Same thing is true of your smoke detectors. They are radioactive. Guess what? You've got smoke detectors in your house, which you do, or it's illegal. There's a little radioactive chip in every one of those. We also irradiate things like mascara, sanitary napkins, baby bottles, or baby bottle nipples, and other things, bandages, you name it, lots of things. But we do use it in lots of food. Don't memorize this, but again, lots of grains, lots of spices, certain meats. NASA uses it extensively because they need to be 10 times more certain that things are clean than we are. Now, what are the nutritional effects of irradiation? Just like cooking, there are some things that go down and people complain, oh my God, it's losing vitamins, it's damaging proteins and enzymes. Well, so does cooking. Thiamine in pork is being destroyed where you don't get thiamine. Okay, it's reducing it, but you lose more thiamine when you cook the pork, and I would not suggest eating raw pork. So again, strange things. Carcinogens. You can make benzene in eggs. That's bad, and I've heard stories about how, oh, you're making a known carcinogen in eggs. You make more benzene by boiling the egg than you do by irradiating it. You make more carcinogens by cooking your meat on a barbecue, cooking your hamburger on a barbecue, than you do by irradiating it by a lot. So again, these are people taking things out of context and trying to scare people when in reality, everything has some level of carcinogenicity or danger to it. It's a matter of mixing things up and being safe and using your brain. It may be able to produce disease-resistant microorganisms. That's one of the almost laughable ones. If we misuse it and we somehow magically create a mutagenic E. coli that's even worse than the E. coli we're facing now, is that possible? It's more likely that you'll watch that in a movie than it'll ever happen in reality. And I'd be much more concerned about human incubators, people who are anti-vaxxers who refuse to do proper, scientifically proven medical techniques. We've got hundreds of thousands of incubators of disease in this country that are spreading known disease. The theoretical idea that somehow you could magically create something accidentally by irradiation is, again, spreading fear. Now, there are 3 levels. You should know these levels: radurization, radicization, and redapertization. Now, these are hard to keep apart, so take a moment before the exams and make sure you remember. Radurization is to reducing the spoilage organisms and extending shelf life. It is not about sanitizing. It's just basically knocking them back a little bit, reducing the numbers. Redicidation is elimination of non-spore forming pathogenic bacteria. It's killing almost everything. It's a pretty heavy treatment. And redapertization is commercial sterilization. It is the equivalent of canning. It's the level of sterilization you would get in a commercial canning process. All right, one more break here.